Today, I'm going to continue to discuss convex separation theorems in Rn. Last time, we proved the following property. Let omega be a non-empty closed convex set in Rn, and let x bar be a point outside of omega. Then we can strictly separate x bar and omega in the following sense. Then there exists a vector v in Rn. Here v is non-zero, such that the supremum of Vx, the inner product of V and x, where x runs in omega, is strictly less than the inner product of V and x bar. Geometrically, this means that if here is a convex set omega that is non-empty and closed, and here is a point x bar that is not in omega, then we can strictly separate x bar and omega by a hyperplane. Okay, so as a corollary, we have the following remark. Let omega be a non-empty convex set and let x bar be a point outside of the closure of omega. Okay, so in this situation, we do not require omega to be closed, but we look at a point x bar that is outside of the closure of omega. So here, omega is not necessarily closed, but we look at a point x bar that is outside of the closure of omega. Okay, then we can still strictly separate x bar and omega. Then there exists a vector v in Rn. V is non-zero, such that the supremum of the inner product of Vx, where x runs in omega, is strictly less than the inner product of V and x bar. Let me go ahead and prove this property. The proof is very simple. So here omega is a convex set, so the closure of omega is also convex. So in this property, we do not require omega to be closed compared with this property. Then we only need to apply the previous property, the previous separation theorem, for the closure of omega and x bar. Okay, so here, since the closure of omega is non-empty, closed, and convex, with x bar outside of the closure of omega, there exists a vector v that is non-zero, such that the supremum of the inner product of V and x, where x runs in the closure of omega, is strictly less than the inner product of V and X bar. Okay? Now, observe that omega is always a subset of the closure of omega. Thus, we have the following property. The supremum of the inner product of V and X, where X runs in omega, is less than or equal to the supremum of the inner product of V and X, where X runs in the closure of omega. And this supremum is strictly less than the inner product of V and X bar. So we have proved this separation property for a non-empty convex set omega that is not necessarily closed, and a point X bar that is outside of the closure of omega. Now I'm going to talk about another convex separation theorem for subspaces of Rn instead of the whole space Rn. In this situation, we have a subspace denoted by L of Rn. Suppose that omega is a non-empty convex set in L. Okay, so omega here is a subset of L. Suppose that X bar is a point outside of the closure of omega. Okay, and X bar is also in L. Then we can separate X bar and omega by a hyperplane in L. Okay, so let me go ahead and formulate this result. Let L be a subspace of Rn. And let omega be a non-empty convex subset of L with X bar outside of the closure of omega and X bar is in L. Okay, then there exists a vector V in L, and V is non-zero such that the supremum of Vx, where X runs in omega, is strictly less than the inner product of V and X bar. Okay, so let me go ahead and give the detailed proof of this proposition. So in this situation, since X bar is not in omega, actually not in the closure of omega, we can strictly separate X bar and omega by the previous remark. That means there exists a vector W in Rn such that the supremum of Wx, where X runs in omega, is strictly less than the inner product of W and X bar. Okay. Here we have a vector W in Rn, but W is not necessarily in L. However, in this situation, we require V to be a vector in L. Okay, so now we're going to use the following property. It is well known that Rn can be represented as follows, as the direct product of L and L pub, where L pub is the set of all X in Rn, such that the inner product of X and A is equal to 0 for all A in L. Okay. So, for example, in R3, if this is the subspace L, then L pub will be the this subspace. Okay, so L pub contains all vectors X in Rn, so that X is perpendicular to every vector in L. Okay, and this notation means that for any X in Rn, X can be represented as follows. X is equal to U plus V, where U is in L and V is in L pub. Okay, so now we're going to use this representation in order to continue the proof. Okay, now since the vector W obtained earlier is in Rn, we have the representation W is equal to U plus V, where U is in L and V is in L pub. Okay. So over here, I will switch the notation a little bit for convenience. So here we can say U is in L pub and V is in L. Okay. Now, so then for any X in omega, then for any X in omega, and here omega is a subset of L, we have that the inner product of U and X is equal to 0. Okay, notice that because U is in L pub, U is perpendicular to all vectors in L. In particular, because omega here is a subset of L and X is in omega, U is perpendicular to X. Therefore, the inner product of U and X is equal to 0. Okay. Then we have the following. If we look at the inner product of V and X, okay, it is the same as the inner product of U and X plus the inner product of V and X. The reason is here the inner product of U and X is equal to 0. Okay, so this is equal to U plus V, the inner product of U plus V, and x. Okay, and as we know, u plus v is just w, therefore this is equal to wx, the inner product of w and x. Okay, so we have the following. Vx, the inner product of v and x, is equal to the inner product of w and x. And since w is in omega, this is less than or equal to the supremum of w, the inner product of w and x, where x runs in omega. And by the separation property we have earlier, this supremum is strictly less than the inner product of w and x bar. Okay, and at this point we replace this by the inner product of u plus v and x bar. Okay, the reason is here w is equal to u plus v. Now this inner product is equal to the inner product of u and x bar plus the inner product of v and x bar. Okay, and because x bar here is also in omega, and omega is a subset of L, this vector v, this vector u is in L pub. So the inner product of u and x bar is also 0, as explained earlier. So this sum is actually equal to the inner product of v and x bar. Okay. So from here, from this estimate, we have the following. The inner product of v and x is less than or equal to this supremum, and this supremum is strictly less than the inner product of v and x bar. Therefore, if we take the supremum of the inner product of v and x, where x runs in omega, it will be less than or equal to the supremum of the inner product of w and x, where x runs in omega, and is strictly less than the inner product of v and x bar. Okay, therefore we can separate omega and x bar by a hyperplane v, and that means a vector v in L, so that this inequality is satisfied.